Hello, and welcome back to the third video in this video series. In front of me, I have the code from our previous videos, so if you haven't checked those out yet, please go ahead and make sure you check those out. So we have an in-detail videos and analysis of what we have done in each of these steps. Today we'll be doing a little bit different, but we will be building off of this code that we already have built. And we'll be dealing with a Bode diagram more specifically. So with that being said, let's go ahead and get started. So what we want to do is create the Bode diagram of our forward transfer function that we went ahead and figured out in our previous video. So very simple. We just simply recall sig, and then we put sig.bode. I'm not sure if it's a capital, I don't believe so. And we put a transfer function tf forward. When we shift enter, we get these three arrays of values. First array is our omega, which is in radians per second, obviously. Then in our second array, we have our decibel values. And then our third array is our phase lag value. So I can go ahead and split this up in three different values, and we can go ahead and plot the two and see how they go with increasing omega, right? So we set our first values as our omega. Our second is our decibel, I'm just call it dB. And then our third value we said is our phase lag, I'm just going to call it phase for now. And we go ahead, phase, and go ahead and shift enter, and now we can go ahead and plot these out, right? So I'm actually just gonna copy this just for time's sake. So we want to make subplots. We want to make, however, two different plots, so we're gonna have to call that. We're gonna have to think rows comes before, and let's make two rows and one column. And then we have to explain what we're adding. For our x value, it's going to be our omega, obviously. And then for our y value, we're going to have two separate values, one of them being the dB and the other one being the phase. Then, of course, we have to tell it row 1, column 1, and then call it name decibel. Let's call it dB. And then we go ahead and do this for the second plot. Our x is still our omega, however, y is now our phase lag. Change the row. And I'm going to change the name to phase lag value. Then, of course, one thing, I'm actually going to make this a little bit bigger so we can see this better. Then also, we need to change our x-axis, right? Currently our x-axis, well, I could show you that it plots nonsense pretty much. Very confusing because we go from 0 to 10 and we need to change our values. So fig.update our x-axis, I believe. Yes. And we want to make it into a log. So I think we just do type equals logarit, and that's all we need to make it a smooth graph. There we go. This is what our graph looks like for our Bode. The x values obviously being our omega in radians per second, logarithmic, and this just disappeared. What happened to our phase lag? Okay, it just disappeared for some reason. And then our phase lag, we can see temperature seems like it is reaching stability at about 180 degrees, right? You could say that. So now the next step that we want to do is we want to determine the amplitude ratio at a frequency of 1 radians per second and compare it against our results from part B2C. So we can go ahead and do that. What we want to do Let's create another Bode, sig.Bode, and again the transfer function forward. However, we want to determine when omega w is equal to 1, right? So if we shift enter, we say we get this value 0.01, and we see the difference or the importance of using our periods in coding, right? So it gives us these values of negative 3.87 and negative 178 for our dB and our phase lag respectively. So now we can go ahead and use these values to determine our AR, which will determine our amplitude ratio. And this amplitude ratio I'm calling AR, something that has been determined a long time ago, and is simply 10 to the power of the decibel value given, which is negative 3.2, divided by 20. So 10 to the power of our dB capital divided by 20. Shift enter and click AR. We get a wrong value. I think I need to put this as W equals to 1 as well. There we go. So we have a value of 249, which is wrong. And I believe this must be wrong simply because, again, the importance of our periods, right? If we click that in, we see the difference that makes and our final value. That looks a lot more reasonable. We get 0.64. So if we go back up or down to see what we worked in our previous video and look at our output, let's see here at the end, we can see that our output is about 0.64, and it reaches, let's see, what is the precise number? We got 0.64031, and we get up to 0.6403, or 0.31 almost. So we can see that this is pretty accurate, and we can actually make it more accurate if we want to, but for this case that's good enough for us. We could have shown that there are two different manners that we can determine our amplitude ratio, right? So we can go ahead and take this value out. We don't need that anymore. We can delete this. Right, and then there's one thing that we want to talk about, and then on our next step, which is the crossover frequency and our phase margin. Two very important things that need to be kept in mind when doing a lot of process dynamics controls, but also with a lot of our feedback information. Excuse me. So, like we said, I want to talk about crossover frequency and phase margin. Well, the crossover frequency is actually fairly simple. So we want to first look at our phase lag diagram, and we know when it's trying to be stable, we see that about 180 degrees and is when it's trying to, it's reaching that stability. So we see when it first reaches 180, which is roughly at about 1.15 to be precise. And then we go ahead and compare that omega value to our decibel values and see what decibel value we end up reaching with that omega value. And depending on whether it's positive or negative, demonstrates whether it is stable or unstable. So for this scenario, or for this case, let's go ahead and do a little bit more precise. We see that it first reaches 180, about right here. It looks like point is 1.15, and we can always get more precise here as well. But let's go ahead with 1.15. And if we go ahead and zoom in on 1.15, 1.15, we see that we get a negative 6.56 value for a decibel, which illustrates that it is stable at the moment. So very simple. If it's negative, it's stable. If it's positive, it's stable. If it's negative, it's not, right? So, and then the next thing we want to talk about is our phase margin. It's a little bit more complicated. However, all we do is look at when our decibel ratio, it reaches 0. And when it reaches 0, we compare that omega value that we receive for that decibel being 0, and we compare that to our phase lag graph. And depending on the value that we get for the phase lag for the temperature, we subtract it from the, in this case, 180, because that is our state stability number. And depending on, again, if it's positive or negative, we know if it's stable or not. So let's go ahead and do that. R0 seems to be intersecting somewhere around here, right? So if we look, looks like it reaches 0 about 0.83, say something like that, right? But it makes quite a big jump, so let's see if we can get more accurate for this. I don't think we can. Let's just do 0.83 for now, right? 0.82. So if we go down here and look at where 0.82 is, it looks like it's along here. 0.5, 0.6, 0.5, 0.7, 0.8 seems to be in here. We get about 173 degrees. So if we subtract negative 180, do negative 180 minus 173, which ends up being negative 180 plus 173 degrees, we end up with a negative 7, which proves that we have a stable graph, right? So through both of these, through both our crossover frequency and our phase margin, we're able to say that this current scenario is stable. However, now if we go ahead and change our Kc value to 3, let's go ahead and see what impact that has on both our these two graphs as well as this other graphs, right? So like we said, we want to change our Kc value to 3, and I'm just simply going to run all after that, right? Everything should be good. It doesn't look like it changed too much, but it did affect it a little bit. As you can see later here, there's a big effect. So let's go ahead and start off with the difference, right? So with crossover frequency and a phase margin. So a crossover frequency, again, what does that look like? So zoom in here, see when it first reaches 180, seems to be about 1.15, right? Say 1.15 for our omega value. So we go look ahead at 1.15. Looks like it's around here. And it looks like it's reaching the negative just about before. So there we go. We see that our before under omega value of 1.3, it is a positive value and indicates that this is an unstable situation, right? And if it was 1.417, that would be a stable situation, right? And then here, we want to go ahead and determine when this reaches 0. We said it was about, what did we say? Between 1.35 and 1.4. So we go ahead in here and see 1.35 and 1.4. See 0.8, 0.3, and we see 0.32 and 0.4 are both over 182. So if we go ahead and subtract those, we end up with a negative 2, and that provides us an unstable value for both our phase lag and our decibel value. And what impact will this have on the previous graphs? Well, as you can see, we can also see that's very unstable from this graph. as it illustrates that it starts oscillating very minimal to not even say 2, and it goes back down. But around 100 seconds, it starts going very crazy and oscillating very high. Very highly. So this illustrates that it will be very difficult for this to trace and to reach stability. And as you can see, this has impacted a little bit as well, with our output coming in as big as 2. So as you can see, our KC value is very important and changed up all our values. Then again, if we go back to our KC value of 1, we should see it run back to normal and have a phase, or our 2 values that we were talking about, be positive or be stable. So with that being said, hope you guys enjoyed this video talking about a Bode diagram and how that helps us determine a lot of information based on, or a lot of information on our current systems. So that being said, thank you for watching, and I'll see you guys in the next and final video.